Well, hello. Welcome back, good people. Today we are talking about Lenz's law. Now, in our last video, we talked about Faraday's law, and before we talk about Lenz's law, I would give myself a quick reminder of what is Faraday's law, and then also what are the different ways that you could change the flux through a loop of wire. We know that there are three ways to change the flux through a loop of wire, and any of those three changes in the flux will result in a current in the wire. So what we talked about last time is that anytime you change the flux in a loop, you actually create a current in the wire. But we didn't talk about which way the current is going. So that is our topic of the day, and that is what we call Lenz's law. Lenz's law is going to instruct us as to which direction the current is going to go in a wire. Let's go ahead and start with an example because the easiest way to learn Lenz's law is through an example. Here's what Lenz's law says. Lenz's law says that the direction of the current that is induced in the wire will oppose the change in flux. Or in other words, the current induced in the wire, I'd write all these words, but I'm going to write it shorthand because my computer is laggy. But the current induced in the wire will oppose, the change in flux. And I'm going to rewrite that a little bit cleaner here. The change in flux. Okay, here's what that looks like. I'm going to draw an example. Suppose that we had a magnetic. Suppose that we had a magnetic. I said it twice. That is crazy. Suppose we had a magnetic field that was coming out of the screen like this towards you. And suppose I took a little, are we not going to work? Hello? Hello? We're not going to work? Is my mouse just going to stop working right now? Oh, nope. Okay, that took about 3 years to load. Okay, so suppose that I had a magnetic field that was coming out of the screen towards you. And let's say that I put a little loop inside of this magnetic field here. Boop, doop, boop. Wow, we're just kind of all kinds of slow today. Let's say that I put a loop inside of this field, like this. If this little loop is inside of this magnetic field, the first question that I like to ask students in class is I say, okay, students, is there a current in this loop right now? And they say, no, Miss Wilson. Because the loop is in a magnetic field, but there is no change in flux. There is flux going through this loop, but there is no change in flux. And because there's no change in flux, then there's no current in the loop. But here's the idea, is that if there were a change in flux, then there would be a current in the loop. Let's go ahead and look at what this would look like. Let's suppose that I went ahead and I just turned up the dial on the strength of the magnetic field here, so I made B super strong. Let's say that I cranked up B and I just made this magnetic field so much stronger here. Woo! Yay! A way stronger magnetic field now. That means that now there's more flux going through the loop. Here's what Lenz's law says. Lenz's law says that the current will be induced in the loop to oppose the change in flux. Here's the idea, is that the loop likes the way that things used to be. There used to be a very weak magnetic field pointing through this little loop, and the loop says, I liked when there was a weak magnetic field pointing through this little loop. That was very nice. And so the loop will try to create a current that undoes the change. The change increased the magnetic field going out of the page, so to undo that, this little loop will create its own little magnetic field that I'm going to draw here. You would not draw this on your paper. But the loop is going to create its own little magnetic field, and the magnetic field of the loop is going to go into the page to weaken the change. The change made the magnetic field out of the page stronger, so it's going to try to make a magnetic field into the page to undo this. Well then, to figure out which way the current will go, we use our right-hand rule. If my fingers are going to point into the page at the center of the loop, my thumb will curl around the loop this way, and so the induced current in the loop will go this way around the loop. Notice, the current in the loop is formed to create a magnetic field that opposes the change. That's the idea of Lenz's law. Let's go ahead and try another example. Suppose that we had a magnetic field, and this time the magnetic field was poking into the board this way, and I had a little loop of wire here, and that little loop was just like this in the magnetic field. Oh gosh, my loops are sometimes incomplete. Okay, there we go. I have a loop of wire in this magnetic field, and let's say that I increase the strength of the magnetic field coming out of the board. Can you figure, or out of the screen, can you figure out which way would the magnetic field go? Or sorry, which way would the current go in the wire? Here's what you would say. You'd say, well, if the magnetic field going into the screen is getting stronger, this little wire right here would want to undo that strength, and so it would create a magnetic field going out of the board. So this little thing, again, I'm going to draw little dots here, but you do not need to draw these on your paper. You can draw them if they're helpful to you, but it can also be very confusing because then it looks like maybe there's like, maybe this magnetic field is going both into the board and out of the board, which is why I use different colors. I keep saying board, you know I mean screen. That's how it goes. Okay, so this little loop will try to create a magnetic field that is going out of the screen to oppose the magnetic field that is increasing going into the screen. Use my right hand rule. If I'm grabbing this loop with my right hand and I want the little pokies to poke out towards me, I see that my thumb points, hang on, wait, let me think about it, counterclockwise to me. So my thumb is going to, the current in this little loop is going to go around this loop like this, counterclockwise. And so that would be the direction of our current. Let's try another one. Let's say that this time you have a magnetic field going into the screen once again, like this. And you have a little loop in that magnetic field. But this time, the strength of the magnetic field is decreasing, so I turn down the volume on my magnetic field and make it weaker. Then which way would the current go? Well, here's what you say. You say, okay, well, this little loop probably would want to get extra magnetic field going through the center because the loop says, I do not like change. And this magnetic field going in used to be strong, so I would like it to stay strong going in. So this little loop will make a little magnetic field going in to help strengthen the field that is getting weaker, to undo the change. I use my right hand rule. If my fingers are going into the screen, my thumb is pointing in the clockwise direction. And so I say that the current here would be going clockwise like this. Okay, let's try one more. Actually, I have like a lot more, but I'm going to try a few more. Here we go. Okay, new drawing. Ah, yes, and that is the bell. A new drawing. Okay, let's try this situation. Let's say that we have a magnetic field that is going into the page, like, oh gosh, nope, not like that. And when I said into, I did mean out of. Let's say that we had a magnetic field that was going out of the screen, like this, and that we had a little loop of wire in this little magnetic field here. Like this. And let's say that what I did is I took this little loop and it started in the magnetic field, but then I just kind of gradually slid it out of the magnetic field over here. And so then the little loop of wire landed over here outside of the magnetic field. What would be the direction of the current induced in the loop? Well, here's what I say. I say that this little loop hates change. And it says, I'm actually going to draw this a little bit bigger so I can draw inside it. Okay, there we go. And it says, I used to be in a place where the magnetic field there was lots of flux going out of the screen. And now I'm in a place where there's no magnetic flux going out of the screen. So this little loop is going to try to make, oh gosh, every single time, man, it just makes these weird streaky kind of line things. And I'm like, none of that, please, just give me nice dots. This little loop is going to try to make a magnetic field going out of the screen. And so in order to do it, what it's basically trying to do is it's trying to recreate the situation that it had over here. When I use my right hand rule, I poke my fingers towards myself and the thumb points counterclockwise around this loop like this, so you'd get a counterclockwise current. Let's try another one. Let's suppose, and this one's going to be hard to do just like on the screen here, so I think I'll also pull up a little I might pull up a little, my own little loop and try to do it in real life, but we'll see how this goes. Okay. Let's say that I had a magnetic field that was going into the screen like this. And I had a little loop that started with its orientation directed. The loop is facing perpendicular to the magnetic field. So first you just get a little side view of this loop. Imagine if the loop, if the magnetic field, sorry, I'm going to make this big. Imagine if the magnetic field was going in, actually I'll do it. Yeah, let's say that the magnetic field is going in towards my face. And this little loop used to be oriented like this, but now the loop is oriented like this. That's the situation. So we start this way, that's like position A, and then position B is like this. Do you notice that there used to be none flux through the loop? Because if the magnetic field is going like this, do you see how none of it is going to poke through the center of the loop? But now there's lots of flux in the loop going into the screen. So here's what we used to have, is we used to have a loop like this, but now the loop is going to go like this. Well, the loop used to have no flux through it, but now it does have some flux through it, and that flux is going into the board. And that little loop would prefer to oppose that change in flux. So it would like things to go back to the way that they were when there was no flux through the loop. So, because the magnetic field going into the screen has increased, it will create a magnetic field going out of the screen like this. In order to do that, we use our right hand rule. My fingers curl out of the screen, and my thumb points in the direction of the current. The current will go ba-doop, 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 that way around in the counterclockwise direction. Okay, a few more examples for you, but they're actually on slides. So let me get those slides all set up and ready to go for you. Okay, here we go. Here's this first one. This one should be a little bit of a warm-up for you. It says a magnetic field B that is decreasing with time. I'm going to go ahead and underline that here because that is going to matter. A magnetic field B that is decreasing with time is directed out of the page and passes through a loop of wire in the plane of the page as shown below. And by below, of course, we do mean above. And that word says above, even though it looks like squiggles. Which of the following is true of the induced current in the wire loop? Go ahead and try this one by yourself. If it's decreasing with time going out of the page, the little loop is going to try to make a magnetic field that undoes that. So it's going to try to make a magnetic field like this that is still nice and strong. And so we'll get a current then. If you use your right hand rule, your fingers will point out of the center of the loop, your thumb will curl around, and we will get a current that is traveling around the loop this way in the counterclockwise direction. That's the first one. Let's try the next one. Oh wait, hang on. Let's go ahead and clear out all the ink. Bye, ink. Okay, next. Oh darn, I don't know how to change my slides. 1 second. Okay, this one is a little bit more difficult. Here we go. Two conducting wire loops move near a very long, straight conducting wire that carries a current I. When the loops are in the position shown above, they are moving in the direction shown with the same constant speed v. Assume that the loops are far enough apart that they do not affect each other. Which of the following is true about the induced electric currents, if any, in the loops? Okay, well, here's what you're going to see. You see that there is no magnetic field drawn on this diagram, but is there a magnetic field? For sure. That magnetic field is coming from this long, straight conducting wire. The first task is to figure out which way is the magnetic field going from this long, straight conducting wire. You're going to use your right hand rule number 1. Your thumb is going to point in the direction of the current, in this case, to the left. Your fingers are going to curl. When they curl into the screen on top and out of the screen on bottom. And so what you're going to see is, wait, where's my pen? Yay, pen. You're going to see a magnetic field that is going into the screen on the top, and that is going out of the screen on the bottom. Okay, now here's the thing, is that the strength of this magnetic field is not consistent across this whole picture. No, there are places where the magnetic field is stronger and places where it's weaker. Do you agree? Right next to the wire, you're going to get a much stronger magnetic field right there and right there. But as you move away from the wire, you'll get a weaker magnetic field. So it'll be slightly weaker up here, slightly weaker up here, and then it will be even weaker up here. So here's what that means. As loop 2 moves along its merry journey, loop 2 does have flux going through it. The flux is going into the screen. But the question is there a change in flux? As loop 2 moves to the right, you're going to see that it stays at the same place here. It stays at the same distance away from the wire. And so the amount of magnetic field that is going through loop 2 stays the same, which means loop 2 experiences flux, but it doesn't experience a change in flux. And so there will be no current in loop 2. That means we can quickly cancel out anything that says otherwise. There is no current in loop 2. Meanwhile, loop 1 is moving up the screen, and as it moves up the screen, the strength of the magnetic field is decreasing as it moves up. It's getting weaker and weaker and weaker, which means there is a change in flux for loop 1. So loop 1 is going to experience a change in flux, and it is going to experience a current. Let's talk about the direction of that current. Loop 1 is experiencing a current going into the page that is decreasing. So loop 1 will try to keep things the way that it is, and it will create its own magnetic field going into the page. The direction of the current, then, we can use our right-hand rule. The magnetic field will go into the page. Your thumb will point in the direction of the resultant current. The current will then go this way on the bottom, this way on the side, this way on the top, and this way on this other side, except that does not look at all like I would want it to. Pretend it's an arrow going down. Okay, yep, arrow. Okay, pretend it's an arrow going down. And you see something that goes in the clockwise direction. That gives us the correct answer here is C. Pretend that's a circle around C. Okay, and last slide here. We'll go ahead and change slides real quick. Okay, last practice question for today. It says a wire loop is rotated in a uniform magnetic field about an axis perpendicular to the field as shown above. How many times is the induced current in the loop reversed if the loop makes 3 complete revolutions from the position shown? The best way to look at this one is really to actually play with it in real life with my little loop here. So that's what we're going to do. Here's what I want you to see. I want you to see that right now the magnetic field is directed upwards, and this little loop is has its direction perpendicular to the direction of the magnetic field. So here's the idea. This loop is going to rotate 3 times. Well, if it's going to rotate 3 times, what we could do is we could figure out how many times the direction of the current changes when it rotates once, and then multiply that by 3 to see how many times the direction of the current will change when it rotates 3 times. So let's go ahead and take a look. At first, we say that the flux through this loop is 0 because it's oriented this way and the magnetic field is this way. But watch what happens as I start to turn the loop. As I turn the loop this way, like this, I increase the amount of flux that is going through the loop, and a change in flux creates a current. As the flux is changing going up, this little loop here will try to make a current that undoes that change. So if the flux is going up, the current is going to try to create a magnetic field that is going down to undo that change, since before it used to have none flux. So it's going to create a magnetic field going like this. Everybody see this? Going around this way, like this, through the center of the loop. So that's the situation at first. That's the first part. But now watch what happens. As this loop turns from here, this loop now has going from increasing flux to, as it turns this way, we have decreasing flux going up. So what this loop will do is it will try to make things the way that it was when there was tons of flux going through the loop. So before there was tons of flux going up through the loop, now that flux is decreasing, so the wire will try to make a magnetic field going up, back up, and the current will go this way. Do you see how the current changed directions? At first the current was going this way, and now the current is going this way. Let's watch what happens as it continues on its journey. When it gets to here, there is no flux. And then as it turns, we increase the flux going up. I want you to watch what happens here. It used to be the case that the flux going up was decreasing, and so the current was going this way. Now the current is going this way, going this way, going this way. Wait, sorry, I'm going to grab it hang on. I got to keep it the same. Current is going this way so that the flux can go up. Going this way, going this way, going this way. Well, when it gets to this position, the flux is now going to increase going up, and so the loop is going to try to make a magnetic field going down to undo that change. But here's what I want you to see, is do you see how before it was trying to make a magnetic field going up, now it's trying to make a magnetic field going down. Do you see how though, because the loop has turned, the direction of the current actually hasn't changed? Because to make a magnetic field going up here, the current goes the same way as to make a magnetic field going down here. So even though the flux has changed directions, before the flux was decreasing going up, now the flux is increasing going up, the direction of the current stays the same in order to undo the change. So first the current is this way in order to create more flux going up, then the current is this way in order to create more flux going down. As the loop continues, once it gets to here, you have tons of flux going up. Then as it continues on its journey, you now are going to have decreasing flux going up, so the loop will try to undo that change by making more flux going up. Before it was making flux going down, now it's making flux going up, and so because it's making flux going up, the current will change directions. So here's what we see. We see the wire making flux going down, then flux going up, then as this thing turns, still keep the current the same here to make, still keep the current the same. Okay, sorry. This one's so tricky for me. My orientations with the hand stuff, that's just challenging stuff sometimes. Okay, here's what we see. First, the flux going up is increasing, so it will create a flux going down. Then when it gets to here, now the flux going up is decreasing, so it's going to flip. Then as it gets to here, your thumb is going to stay pointing the same direction like this, but now your fingers are pointed this way. Then as it gets to here, you change direction, and so the current changes direction twice. Tricky problem. We will actually take a greater look at this problem in more depth when we get to generators and transformers and motors next video. But here's what you should see is that the current changes directions twice per rotation. So for 3 rotations, that means that the current changes directions a total of 6 times. And so the correct answer for this problem is 6. Challenging one. I would highly recommend taking a hair tie or getting a loop of your own and seeing if you can't do this whole loop with the right hand rule and testing it with which way your fingers are pointing every single time. Following along and then trying to reteach it to yourself or reteach it to a friend. That is going to be for sure the best way to learn. So practice this one. And that is all of our practice problems for today, folks, and actually everything that we have. The biggest and most important thing of today was learning about Lenz's law. Let me go ahead and get that pulled up here. Okay, there it is. The biggest thing to remember for today is Lenz's law, that the direction of the current will be such that it opposes the change in flow. Oh my gosh, we lost our little circle around the middle there. The biggest, most significant part of the biggest topic of the day is Lenz's law, which is that the current that is induced in a wire will be such that it opposes the change in flux. If the magnetic field increased, it's going to make an opposing magnetic field. If the magnetic field decreased, it's going to try to make a magnetic field that is going to reinforce that decreasing magnetic field. So it is going to undo whatever change in flux that little wire experienced. That means that the direction of the current can then be found using the right hand rule, with your fingers pointing in the direction of the current that is made by the wire and your thumb pointing, direction of the magnetic field that is made by the wire and your thumb pointing in the direction of the current. And that's all for today, folks. I hope you have a wonderful rest of your day, and I will see you next time. Bye, good people.